Okay, guys, I think we can start the session. So, if you attended the last session, like we have been discussing about different SLAM algorithm. We have started from G mapping, then we have seen cartographer, and today we are planning to discuss about the Hector SLAM and Carto SLAM, and then we will be discussing some uh, 3D SLAM techniques. Okay, so let me comment it in Discord. Okay. Okay. So first, I think we can jump into the Hector SLAM. Okay. So let me share the link. I think this is official Hector SLAM package wiki page. So I'm just sharing it. I think you can able to see the link. So what is the difference? Like we already seen the cartographer, then the G mapping. So what is the difference in the Hector SLAM? So there is one main difference in Hector SLAM that I noted was like we don't need the odometry. We can even work without the odometry. So I think maybe I can show you this video. It's actually a mapping of an area, and you can see here there is a handheld device. Okay, uh, a person is actually like carrying a handheld device, and it is having a laser scan on the top. You can see here, right? There is actually a laser scan, and there is nothing other than that. So he's simply walking, and you can see uh, this this frame, right? This frame is actually moving. So that means it can compute the odometry. Like for the robot, for the turtle board 3 and all, it can compute the odometry from the wheel encoders. But for this setup, there is no wheels. The person itself only carrying it. Okay, so if it moves, then you can able to find the setup is actually moving, and also it is creating the map. And I think this person is actually going through a maze actually. Okay, and uh, and you can see on the right side uh, it is creating the map. Okay, yeah, it is completing the map. Okay, so like he actually entered through this point, and then he returned through that point. Okay, so this this SLAM algorithm is actually completing. There is a word called loop closure. That is what yeah, I think that is what this terminology. Um, like what I understood was like if you take this example now, let me take it again. If you take this example, this person actually start from here, right? And then he actually went through this space, and then he returned to the same point. So the map is actually closing. Map is not creating. I mean, if if we consider the map and also the reality, both are same actually. Okay, I think that is actually the loop closure. So Hector SLAM is actually doing that without any odometry, with only using laser scan. Okay, so that is one advantage that I have seen with Hector SLAM. And another thing is that like the application, the usage is mainly into drones. Okay, so in the wheel robots, no, for the wheel robots it may have odometry and we can use it, but for the drones, for the 2D mapping, uh, it don't have any kind of odom. Okay, but if it is only having laser scan, you can simply create the map using this. Okay, and like if you're currently using Hector SLAM now, if you want if you're currently using G mapping, then you can simply switch to Hector SLAM. Okay, by doing this configuration. Okay, so like um, simply by changing the parameters, we can able to set the G mapping into hectare slam. So this is actually showing the setup without, I think, without odom frame. Okay, so you don't need the odom frame. So the difference with the G mapping and hectare is maybe these values you can check. Um, for the G mapping, publishing map to odom transform. Okay, yes. Uh, okay, so it's saying like in order to compatible with G mapping, we have to set these parameters. So maybe I just want to go to the G mapping again just to mention a simple thing. I think I have missed in the explanation. Let me just go. Yeah, maybe I can run it and explain. So let me run the simulation, and after that we can come back to the hectare slam. Okay. So first I'm starting the simulation of turtleboard. Uh, I'm also keeping the slam launch file. So let me start the turtleboard simulation. Turtleboard 3 world. Okay. And starting the, okay, it's getting started. And I'm starting the slam. Okay, so it started and RVC is popping up. Okay, so if you take the RQT, okay, if you take the RQT graph, you can see here, just a second. I'm just putting the TF tree, and you can find here. So the this is a TF tree. Okay, this is a TF tree of the G mapping. I mean, when you run the G mapping, you will get this TF tree. Okay, so before that, it will be like the robot URDF. Okay, the robot URDF is having the TF from the base footprint. Okay, so from the base footprint to base link and all the joins and links of the robot. But what about the ODOM to base footprint? It is actually publishing by the driver. Okay, ODOM is computing by the driver program, which is actually listening to the wheel encoder's value and then computing the ODOM and publishing the TF. What about map to ODOM? So this is what happening when we run the G mapping. So once we run the G mapping, and in order to make sure all these TF is correct, you can see this thing, map to ODOM. So this transform, no, this map to ODOM is actually publishing by what? It's publishing by G mapping node. Okay, so this is a transform that we are getting. So with respect to the map, where is the robot? Okay, where is the robot? That is what we are getting. Like when you move the robot now, with respect to the map. Okay, with respect to the map, where is the axis of the map? So if you check, this is the axis of the map. Okay, and we are also setting the fixed frame here. You can see here, this visualization is actually showing with respect to the map. Okay, so with respect to the map, we can see the robot. Okay, and this is actually doing by the G mapping node. So if you just go to the G mapping wiki page, you can able to see the G mapping node obviously publishing the map, but other than that, it is also publishing the map to ODOM frame. Okay, so that is the current estimate of the robot pose with respect to the map frame. Okay, so I just switched to that because here they are also saying G mapping publishes map to ODOM frame. Okay, So you have to set the following parameters to reflect the setup on your robot. So if you want to make the robot compatible with the existing Hector SLAM, then you have to set this parameter. Okay, then launch the Hector SLAM. So I will be going through that. So it seems like there is a parameter called pub map odom transform. So this is actually responsible for publishing the map to odom frame. Okay, so I think that's why we need to set up these parameters. And if you don't have any odom frame, imagine if we don't have any encoder data, we only have the laser scan, then we can set this. So the difference is that here the odom frame is actually set as odom, but here the odom frame is setting as the base frame. Okay, so if you don't have any odometry, or if you have any other source of odometry, I think you can simply set this parameter to get start with the mapping. Okay, so I'm just quitting the SLAM, and then let the simulation run. Okay, and now what we are doing is we are planning to start the Hector SLAM. Okay, so Hector SLAM, if you just go through the package, it's actually very similar setup like Gmapping. There is a node and we have to configure it. So this is the Hector mapping package. Okay, and this is having a node, and you can see here it is subscribing to laser scan and some reset command, and it is publishing the map. Okay, so that is the input and output, and also there is an option to reset the map. So it is having ROS services in order to reset the map. Okay, that is also there, and a tons of parameters. Okay, so it can also provide map to odom transform. So there is another video again that is actually showing from the handheld device. We can simply check it. You can see there is a handheld device, and the person is moving, and on the right side the map is getting created. So there is no robot actually. I mean, we can simply create the map with this setup, and it's also accurate. I mean, you can see here the mapping is not bad. Okay, the mapping is good only, and we are only relying on the laser. Okay, so this is how the Hector is working. So here he is demonstrating the loop closure. Like he start from this point, and he is going to the same point, and the map actually completes. Okay, that means it is coming to the actual point. See here, he is returning to the actual point that he started, and yeah, so it's very accurate. Okay, yes, so maybe we can see like how we can set up these Hector SLAM node. We already have the launch file, so I'm just going to the Turtleboard 3 SLAM package. Yeah, and just going to the launch file, we can see here the Hector.launch, which is actually starting the Hector SLAM node. So you can see here, this is where we are starting the Hector SLAM. Okay, you can see here from the Hector mapping package, we are starting the Hector mapping node. Okay, this is executable name, and this is the node name. I mean, you can give the any node name. This should be always be same, like the package name and executable name. Okay, and here you can see we are using the ODOM frame. That's why we are putting ODOM, so ODOM frame. Then also the base frame for Turtleboard is the base footprint. Okay, base frame. And then we are also setting the scan topic, map size, then pub map ODOM transform, all these things, and we are taking that inside to the node. Okay, so here you may have some confusion, like this is how we are starting the node, right? And these are all private parameters. Okay, these all are private parameters only applicable to this node. So if you check this launch file now, this node is actually ending here. Okay, this node is ending here, and yeah, this much. Okay, so in this launch file, we are basically launching the Hector Slam. Okay, so how to start this? Maybe we can use the turtleboards slam.launch, and you can just give the slam methods as Hector. That's it. Okay, so just taking the launch file, and then in the slam methods just give Hector. Okay, let's see whether it's work or not. Seems like it is running, and here it is. Okay, so it's creating the map, and what we are doing is first we can start the RQT. So RQT is here, and you can see the TF map to ODOM to base footprint. That is correct. Then if you check the nodes, introspection, node graph, you can able to see this is the Hector mapping node. Okay, and what is the input and what is the output? It is subscribing to TF, and there is a scan that is subscribing, and we have the map topic that is the output. So what I'm doing is I'm just loading the robot tools, which is the robot steering, and I'm just driving the robot. Let's see how it is creating the map. Seems like it is creating the map very similar to the G mapping. We can't distinguish between this mapping algorithm, right? It's fast, but one of the practical issue with the Hector Slam is that like there can be orientation error. For example, if the robot is rotating quickly or robot is rotating fast, then I think this can lose the orientation or the localization. Localization means like if we can compare the actual robot pose in the environment, and if we can compare the actual map pose, okay, then if it is same, then it is correct only. Okay, but sometime this localization can have some issues. Okay, so then yeah, then maybe you have to reset or we have to restart the map. Okay, so you can see how quickly it's created the map, and it's very simple to configure. Just run a launch file with some parameters, and you can able to run the Hector Slam. Okay, yes, so that is the Hector Slam, and in order to save the map, we can use the same command. I think we already used that for cartographer and yeah, G mapping. So just going to the desktop, ROS1, map server, map saver, and -f. Hector map. I'm just giving a map name, and then yeah, it's got created. And if you just go to the desktop, you can able to see the Hector map here, and this is the map that is created. Okay, and also we can see the YAML file, the origin, and also all the parameters. Okay, so I think that is a Hector Slam. It's very similar to the G mapping, but there is advantages, like we can able to work without the order. Okay, yes, so that is the tutorial is available. And next we are jumping into the last 2D slam that we are taking in this class, that is a Kato slam. Okay, slam Kato package. So I'm just sharing the link. And the slam Kato package, I mean, algorithm wise, like it is more robust than the G mapping. Okay, maybe I can just talk about the background. So just a second. Kato slam. Yeah. Yes. Yeah, I think that is the same. I think this is the Kato slam package, but I'm just searching one thing. Yeah, Kato robotics. That's what I was searching. Just a second. Yes, I think currently the website actually changed. I mean, yeah. So maybe I can talk about the background. So there was a company called Kato Robotics or something that was actually in US. So they actually created this SLAM algorithm for mapping big environment. Okay, and it was actually proprietary, but then I think the company actually shut down, and the current um, Slam Kato package. What happened was these Kato algorithm, Slam algorithm, they got open sourced. Okay, so after that, the ROS team actually created a wrapper around that Kato mapping library. Okay, so the foundation is the Kato mapping library. So if you check Kato mapping library, yeah, I think this one. So this is the Kato mapping library, separate library. It is an independent library. And the Slam Kato is actually the ROS package, which is built around this Kato library. Okay, and from my understanding, the Kato Slam can use for big areas. Okay, like there are some limitation in Hector and G mapping. Sometime it may not work with the big area, like if you plan to map a warehouse or something. Sometime it will fail. Okay, sometime it's not, sometime most of the time it will fail. But this G mapping and Hector is actually suitable for like medium sized area, like we can map it without any problem. But Slam Kato, I think it will work well with big area. Okay, and there is a Slam toolbox which is actually maintaining by Steve McKenzie. I think some of you may heard about Steve McKenzie. He is actually the original creator of the ROS2 navigation stack, and he also like created this Slam toolbox. So in Slam toolbox, I think they are using the Kato Slam. I think uh, yeah, you can see here, um, the scan matcher of Kato is, yeah, I think they are using the Kato slam. So that is what my understanding is. The slam toolbox. So slam toolbox is basically, maybe we will see that in ROS 2, like it's basically for managing the map creation. Okay, so this is an important package, but currently they are mainly working on the ROS 2. Okay, so it will be better to discuss that on ROS 2. Yeah, yes, so this is a Kato SDK that is for the mapping. I think we will be seeing this. So yeah, so coming back to the slam Kato. Um, so if you check the input and output, it's the same. Like with the G mapping, it's the same. Like it is subscribing to TF and scan, and it is publishing map. So in order to switch between G mapping and Kato, it's very easy to do. Okay, so there is nothing to discuss, just feed the input and we will get the map. So we can quickly do that, and also in order to install this package, no, I think better will be installing Synaptic Package Manager and just search for this name. Like if you want to okay, so I think there is some problem with the Synaptic. Let me check. I'm not sure. Oh, okay. Let me just fix that. So it's very simple. Like just go to the Synaptic and search for these packages. So I think you can simply install it. It's very easy to configure. Let me just update it, and then I can show you how to install the Hector Slam and Kato Slam. Okay, just a second. And you can check the launch file. It's in the Slam package. Just take the Slam package and you can check this Kato launch file, which is very easy to understand. You can check here. Just a second. So you can see here we are starting the Slam Kato node. Okay, and we are feeding it with some parameters. Okay, which is Kato mapper parameters. So which is in the config folder. So these are the various parameters for this algorithm. So we can simply fine tune it, and yeah, that is only the things we need to do. Like just pass these parameters, and yeah, it's ready to go. Okay, so I can show you how to install it. Just take the Synaptic and let me check whether it's working or not. Okay, if you are getting this error, I think you can first try with deleting this file. Again, I'm trying. Yeah, I think it's coming. So just search for Hector. So you can see here we have ROS Noitic, Hector Gazebo, Hector plugin. So this is another Hector. Okay, what we want is the Hector mapping. Okay, so that is already installed. Maybe we can upgrade or update. So this is what we need. Okay, the Hector mapping. And there is a Hector Slam package also, so that will be installing all the packages like mapping package, map tools, all these things. Okay, so if you want to install Hector, that is it. And if you want to install Kato, just search for Kato. You can see here the Slam Kato package, which is already installed, and Slam toolbox. Okay, so these thing, Open Kato is the C++ library that we mentioned. So the Slam Kato is actually the wrapper. Okay, wrapper of Open Kato. Okay, so maybe what we can do is we can again test the Kato Slam, and then we can switch to the 3D. Okay, so we can't able to run the 3D, but we will just go through it. Okay, so this is the simulation, and let's start the Kato Slam by just passing the Kato. Let's see if it work or not. It seems like it is taking, and we are just start getting the map, and let me take the RQT, and we can simply move the robot. We can see, I mean, the map creation is almost almost the same, and yeah, it's almost the same and also accurate. It's not bad. Yeah, if you compare with the robot position with the map and with the gazebo, it will be almost the same. Yeah, so currently robot is here, and with respect to the map it is here. Okay, so we can just confirm that the mapping is accurate, and also we can double check the mapping, like if it is mapping correctly or not, by checking the laser scan. Okay, like if the laser scan is having some mismatch or something, then you can confirm there are some issues. Okay, yes, so this is the Kato Slam. I think it's also building the map very nicely, and we can able to see the RQT graph. So just open the node graph, and you can find the main node, which is Slam Kato. The input is the TF and the scan, and the output is map. Okay, and if you visualize the TF tree, you can see the same TF tree. Okay, so here the map to ODOM is actually publishing by Slam Kato. ODOM to base footprint is actually publishing with the driver. Here, instead of driver, the gazebo plugin is doing, the differential drive gazebo plugin is publishing the ODOM to base footprint, and other frames are publishing by the URDF. Okay, yes, so I think we have simply covered some of the existing 2D Slam, and now we can switch to some 3D Slam discussion. Okay, so I'm not sure I can able to run these thing. Let's see. So the first 3D Slam that we are discussing will be RTAB. Okay, RTAB is actually quite famous. We can see some videos first, then you will get an idea. Okay, just a second. So let me share the link. So this is a 3D Slam. Okay, 3D Slam, or we can say the RGBD Slam. I will be explaining. Okay, so from the wiki page itself, we can see it's not, I mean, it's actually like very big wiki page. You can see a lot of videos added and a lot of instruction, and if you simply scroll through this, you can find a lot of information. Okay, so that means this package is actively maintained. Not only this package, the library itself. Okay, so some information about RTAB is actually given. It stands for real-time appearance-based mapping. Okay, and it's giving, it's already given. It is actually RGBD, stereo, and lidar graph method SLAM approach. Okay, so the RGBD, I think you already know, like the depth sensors now, the Intel RealSense. So we can say that these RealSense camera, it's a RGBD camera. RGBD camera in the sense we will get the RGB data and also the depth data. Okay, and along with that, we can compute the point cloud, that is a 3D data, 3D image data. It's not image, but the 3D information of the environment. Okay, I think you already know about the point cloud. So that kind of data we can use for this SLAM. Okay, and so that is one kind of sensors that we can use. And you also know the stereo cam, right? So this RealSense, no, this RealSense camera, these cameras are RGBD and also stereo camera, because this RealSense cam can be operated in two modes, I think. So here maybe I can open, yeah, you can see here, this is the RealSense camera diagram. So you can see here there is a right imager and left imager. Okay, so I think you heard about the stereo cam, right? Our eyes are like a pair of stereo, like a stereo cam, like two cameras separated in a specific distance. Okay, so the stereo cam in robots are a copy of our eyes. Like we have two eyes separated within a distance, and with these two eyes, by combining these two eyes, we can extract the 3D information. Okay, so yeah, so there is a question from Tejas. Does RTAB have VSLAM? So actually, from my understanding, visual SLAM, okay, visual SLAM is actually the general terminology for, I mean, we can include RTAB in the visual SLAM category. Okay, because it's a vision based SLAM. Like we are using the RGBD data and also the image data, so it is actually taking care of, I mean, it's actually make use of the vision. Okay, so from my understanding, we can include the RTAB in the VSLAM. Okay, because it's taking care of the image and the features as well. Okay, so maybe I can double check and I mean get back, but from my understanding, it's actually the visual SLAM itself. Okay, so we are using the RGBD data, then stereo cams, which stereo vision, and also it's saying we can even use lidar. Okay, so these are some of the inputs to this algorithm. Okay, and obviously it is creating the 3D map instead of the 2D map. Okay, so this website now, this introlab.github.io. So this is an official website. So in this website, they are mentioning the base paper, okay, base paper, and similar SLAM algorithm. So here you can see here RTAP map as an open source lidar and visual SLAM library for. So there are some base papers available, and this RTAB library, this library is compatible with all the operating system. Okay, so we have seen in the CartoSLAM, which is actually a wrapper, the ROS package called SLAM Carto, which is actually the wrapper of a library called OpenCarto. So same thing is here. There is an RTAB library, And this RTAB ROS, no, RTAB ROS is actually the wrapper, okay, or the uh, yeah, it's based on this C++ library, okay. And let me check the, yeah, so this is the RTAB library GitHub. This is a standalone library. You can see here it's a map library and it's standalone. So if you want to use ROS, then there is a separate package or separate repository. You can see here, this is the ROS wrapper, okay. So we will be working with the ROS wrapper anyway, and yeah, yes, GTSAM. Okay, just a second. Yeah, so I think if you remember, I have mentioned about a library that I was like looking for. So this is the library. I'm not sure you remember that. I think I have talked about a graph-based library, which is actually using to factor graphs. That is the word, factor graphs. So this is, I mean, these technologies using in new SLAM algorithm. So maybe I can say something about it. Frank Delaware. Yeah, this is the guy. Just a second. Yeah, this guy. So actually, I have attended a session of him. That's how I got the idea of the factor graph. So I think these RTAB, no, RTAB can use this kind of library. It's like optional library, like we can use this as an option. G2O, I think we have seen already. I think GTSAM is what the optional library. We can use it as a backend, okay, like the library to hold the features and all. So coming back to Frank Dellard, he's actually a pioneer in this field, SLAM. So he's one of the advisor for the that product, Skydio. Okay, so that's how yeah, that's how he got famous. And like you can see here, his advisor is Sebastian Trun, and his main area is factor graphs for perception. Okay, so this person, I just want to introduce, like along with learning concept, you can see here, and he actually got the PhD from Carnegie Mellon. Okay, so he actually there when I was in CMU for a talk actually. So here you can see in 2015-16 I served as a chief scientist at Skydio. So this is what I mentioned about, like when we have seen the Skydio drone, uh, yeah, the demonstration initially, I talked about this, right? So yeah, so this product actually, the foundation actually created using GTSAM. Okay. Yeah, and currently I think he worked with the Verdant Robotics. I'm not sure. I heard about it. Let's see what they are doing. Yeah, it's again some kind of mapping thing. Verdant Robotics. Um, it's for agriculture, I think. Yeah, agriculture robotics. So he's currently into this. Okay, and you can see his citations, its index and all. And I think his main he have done his PhD under Sebastian Trun, I guess. Yeah, yeah. So this was one of the key package, guys. It is actively maintaining GTSAM, and we can use that GTSAM in RTAB, okay, as an optional dependency. Okay, so in order to install the RTAB on ROS, I think you can either install everything from the GitHub. Okay, the instructions are directly given. So the RTAB is available for ROS 1 and ROS 2. So just clone it and then you can simply build it. I will prefer the binary installation, so we can do it very fastly. So just searching for the RTAB in the Synaptic, and let's see if there is any RTAB package. Okay, so we have to look for the ROS package. Yeah, so ROS Noitic RTAB. Okay, so this is the library, it seems, and we need to install RTAB ROS. Okay, so this is the package that we need to install for the RTAB. I'm not installing it now because there is a space issue for this VMware, so I'm not installing. So we can simply install RTAB ROS using this command. Okay, so after installing, you can directly start the RTAB using the launch file. That's how it is. Okay, there is no other complexity, but I can discuss where we need to spend time on RTAB. Okay, so that will be, so you got an idea, right? Like what is the RTAB about? It is actually RTAB map is a I mean standalone library, and RTAB ROS is actually a wrapper, and there are some optional dependency like GTSAM. So then we have seen who wrote the GTSAM. It's Frank Dellard, and he actually the chief scientist at Skydio, and he also yeah, he was a professor and also did PhD from CMU. Then in working with CMU, he worked with many pioneers like Sebastian Tron, and then he worked with Georgia Tech, and then currently he's working on Verdant Robotics. Okay, great. Yes, so I'm just closing this. So just remember the factor graph. Okay, factor graph. Okay. Okay. So coming back to the RTAB ROS package. So basically, so if we are working with the RTAB, we already seen we can interface multiple sensors into it. Okay, multiple sensors into it. We can interface a depth sensor, depth camera like RealSense. We can also integrate a laser scan. Okay, so there is multiple options to add different sensors. Okay, you can integrate the stereo cam, and you can integrate even LiDAR. Okay, I have worked with the Velodyne LiDAR along with camera. So there is a sensor fusion, like we can fuse the camera data into the Velodyne, and then we can use that into the RTAB for creating the map. Okay, so I will discuss that. So first we can see a video. Okay, we can see a video. So here, yeah, let's see the video. After that we can discuss. So seems like they are using a depth sensor, depth cam. So on the left side, it's RGBD, right? So there is vision from the camera, and also the 3D point cloud, the depth image also they are taking. So on the left side, on the right side, we can see the map is getting building. So seems like this video, I think they are only using the images. Okay, I think only using the images it is creating. So on the left side you can see it is detecting something. Those are the features. So seems like, and on the bottom there is a frame actually moving, which is actually the visual odometry. So whenever whenever the robot is moving, it's creating the odometry, and also it's creating the 3D map of it. So it's also having loop closure. I think it may be using the point cloud, but let's see what are the things they are using. Yeah, so seems like these you can actually try it out. Okay, maybe what we can do is, yeah, there is an idea. What I can do is I can remove the cartographer to save some space, and let me check. I can run this thing, cartographer ROS, or the Carto workspace. Let me check the size of it. Yeah, it is having 304. Okay, anyway, what I will do is I will install the RTAP and check what will happen. So simply I'm installing RTAP ROS. Wait, RTAP map ROS. Okay, installing. And at the same time, what I'm doing is I am downloading a back file, okay, which is around 295 MB, and this back file is having the necessary data that we want. Okay, one of the configuration, like it is using camera frames, and also the depth image. There is another back file here which is also having the same thing, and there are different back files here, so which is having different sensor data. So if you don't have the sensors with you, you can try it out using the back file. Okay, so let me see. I can use any of this back file. Maybe, yeah, maybe this I can let me try to download this. So I installed the RTAP, and yeah, let me try to download. So you will also get a clarity. Let me see whether it is downloaded. Okay, yeah, it is downloading. So we can just have a look onto the RTAP now. Okay, let me close all this stuff. Okay, coming back to RTAP. Okay, yeah, yeah, it is downloading. It's taking some bandwidth, that's why. Okay, 20 to 20 second left. I'm just, because this RTAP ROS package, no, the wiki page is actually very lengthy. So let me just scroll down at the end, and we will get the input and output to this. Okay, got it. So here it is. If you just go to the RTAP ROS package, you can see the nodes. Okay, so first is the RTAP map, which is a main SLAM node. Okay, and for this RTAP node, we can add a lot of parameters. So these are the subscribed topics. It can subscribe to odometry, then RGB image, RGB camera info, depth image, scan, point cloud, If it is a stereo cam, we can use left and right camera image. Then I think goal, that I'm not very sure. It's plan a path to reach the goal using that, not very familiar. And it can also use the RGBD image. I didn't use this, but let me see what is an RGBD image about. Okay, so the RGBD image is having the RGB image, depth image, then the features. Okay. Oh, that's great. Okay, so we can simply provide this RGBD image topic. Then it can take IMU value, it can take GPS, it can take global pose, uh, fiducial transform. Okay, so there are a lot of inputs to it. And what are the output? The map, obviously the map, and also it can create the 2D map as well. Okay, not only the 3D map, it also can come up with the 2D map. So here you can see occupancy grid map. Okay, then cloud map, which is a 3D map, which is in point cloud, and scan map. Okay, so then octomap. Okay, so you may be confused. So it is publishing a lot of thing and it's subscribing a lot of thing. So how we can configure? So the configuring of these RTAB is happening through the parameters. So you can enable maybe stereo cam, we can disable it. So all these things can be done using the parameters. Okay, and there is a tool as well, but we can do it in RVs. There is RTAB Viz, which is dedicated for RTAB mapping. So basically, I think you got my point, right? Like there are set of input and there are some output. So you can switch it on, switch it off. Like if you want to take the RGBD data, just switch on it. Okay, and then if you want the 3D map, just switch on it. Okay, so like that, there are multiple options in this page. Okay, so the configuring is actually the difficult part. Okay, we have to configure it. So that is what the difficult part according to me. Yeah. So there are some other nodes available for syncing and all. There is some nodes available like point cloud to depth image, like we can convert, then point cloud assembler. So these nodes can help you to play with the point cloud. Okay, so maybe first, okay, we can work with this back file. Okay, just a second. So I'm just closing this. Back to the demo page. And yeah, so this is the launch file they are asking to start. So in this launch file, I will come back to the launch file. So let's see. Let me close this. Okay, I'm starting the launch file. We already installed the RTAB. Okay, so we can launch this, and now we have to start this back file. Yes, so now we can check the RVs. You can see here it is creating the 2D map. Okay, and there is a problem with the 3D point cloud. It's showing the error. I'm not sure why, but it can also create the 3D map in parallel. Okay, I think because of the frame. No, I think it's okay. What is the error it is giving? Failed to transform open and okay. I think there are some frame issues. Okay, but seems like it is creating the map, but the 3D map is not creating. I mean, it's creating, but it's not visualizing. uh, yeah, anyway, I think you got an idea, right? Like if you just check the topics, ROS topic list, you can able to see the input from the back file, which are like the images, then the odom, all this stuff. Using that, we are creating the 2D map and also the 3D map. Okay. Yeah, so Tejas, I think I have mentioned that like the point cloud is actually showing an error. Okay, I don't know, like there are some frame issues. It may be, yeah, you can see here on the left side. Actually, we are getting the point cloud. You can see here, it is receiving the point cloud, but there is a frame issue. Okay, so maybe we can visualize, but let me check. Failed to transform OpenNI optical frame. So maybe we can visualize it. Maybe if you check the OpenNI optical frame, just a second. Okay, there is no OpenNI optical frame. That is why that error is coming. So I think there are some changes in the code. Okay, so what happening is that this point cloud, no, it actually require a transform from OpenNI RGB optical frame. Okay, but that is not there. Okay, RGB optical frame, let me see. Yeah, that is not publishing or something. I think there is a TF issue, so we can only visualize the 2D map. Okay, and let me just take the RQT. So RQT is slightly complex. You can see here uh, the same frame map to odom is publishing by RTAP, and then odom to base footprint is actually getting from the back file, and all these things are the TF of the robot. Okay, so yeah, so I think there is a frame issue actually, so that's why it is not visualizing. Yeah, so what you have seen was a basic demo of RTAP. Okay, we can simply see the launch file, so nothing complicated. If you compare with gmapping, then Hector Slam, what we have seen was we are simply starting a node. Okay, the mapping node. Same thing here. We have the RTAP map node, which is doing all this stuff. Just feed with tons of parameters. Okay, so this node, this is actually for the visualization. Okay, we can ignore it. Okay, so instead of RTAP vis, we can use the RVis. Yeah, so this is for the RVs. So there is an option for us to select what kind of visualization we are preferring. Okay, so this is a main node, and you can see a ton of parameters, like what is the odom frame ID, then what is the, I mean, are we going with the stereo cam or point cloud? I mean, whatever the input we need to get, we have to enable it. You can see here, subscribe to depth set to true, subscribe scan set to true. So like that, switching on switching off kind of thing, we can enable and disable. So initially when you start it from the scratch, you will get some issues for sure, but I will prefer to start from the existing launch file. Okay, because from the wiki page itself there is a ton of parameters. Okay, so understanding all the parameters and tuning from the scratch is actually painful. So by taking from an example like this will be much faster, I will say. Okay, so there are so many references here for the launch file. So imagine if you want to work with um, some kind of devices. I think there are some um, references. Okay, already references available, so you can take that. Yeah, so that is actually the RGBD, sorry, the RTAB map thing. Like you can simply go through this page. Basically, we need to do the configuring of the parameters. The launch file is actually there, but we need to configure. Okay, so there are many um, videos also uh, added. Yeah, okay, so this is RTAB. I just gone through some abstract idea of it, that's it. Okay, yes, so now I'm planning to switch to the last thing, that is HDL graphs lab. So I'm planning to just talk about it and then we can end. Okay, end the session. So if you want to create the 3D map um, using the lidars, okay, 3D lidars, I think one of the option is the HDL graphs lab. Okay, HDL graphs lab. So so in the self-driving cars, mostly one approach I have seen is that in order to create the realistic 3D map, what they are doing is they are taking the images from the stereo cam and or some RGB cameras, and they are fusing this camera data into the Velodyne point cloud. Okay, so like image fusing with Velodyne lidar. So this is what I am talking about. uh, we have the Velodyne um, point cloud, but the problem with the Velodyne point cloud is that it doesn't have any RGB data information. Okay, so if you want to add the RGB data information, you have to do the image fusion, okay, with the point cloud. Okay, that is actually somewhat difficult because we need to calibrate these things and all, then only we can fuse it. Okay, so after fusing, maybe we can use that fused point cloud into RTAP, maybe for creating the 3D point cloud map. Or maybe if you are not having any image or something, you can simply use that 3D lidar uh, for creating the 3D map like this. It doesn't have the RGB content, but only the map, 3D map. So um, it's actually like everything is given here. The node input and node output is already given, and in order to install and test, there is back files available. So we can see some, let me see if there is any video. Just a second. Yeah, maybe I can, because I can't download the file. Maybe I can start explaining and let's see. Okay, so there is a question from Tejas. When robot is localized and it is moving, TF3 should show map to ODOM, right? Or that is required only during mapping. Uh, should show map to ODOM. Let me check. TF3 should show. Yeah. Uh, no. Yeah. So what Tejas mentioned was, the question is. So we have seen the TF3 when we run the G mapping. We got the TF3 like map to ODOM, ODOM to base footprint to base link. So that we have seen in the the mapping. So the SLAM algorithm can do the mapping and localization. Okay, so the map to ODOM actually showing where is the ODOM frame with respect to the map, or where is the robot with respect to the map. Okay, which is also showing when we localize. Okay, so this frame map to ODOM frame will be also published when we do the localization. Okay, that is if you check the AMCL package, you can see the AMCL can also publish the TF. I think on the bottom, I think they are talking about, you can see here, map to ODOM frame. Okay, map to ODOM, I think it can publish. Okay, but from AMCL, I mean ODOM to base footprint, I think it will be there. The AMCL can compute map to base footprint, I think base frame. So you can see here. So then when we run the localization, we will have the TF tree, like map to ODOM, ODOM to base link, like that. So this frame, I mean the TF publishing will be there for mapping. That is not that we are giving. It is actually publishing by SLAM algorithm and also the localization algorithm. Tejas, is that clear? Okay, I think yeah. Okay. So now going back to the graph SLAM. So I'm just giving an idea, and then you can check. So for this graph SLAM algorithm, we can use the 3D LiDAR. Along with that, we can use GPS IMU, okay, which is actually given here. And for this algorithm, maybe we can test it using simulation, or there are some back files already. So they have tested mainly with the Velodyne HDL32E and VLP16, and also some RoboSense LiDAR. So here you can see like everything, this SLAM algorithm, everything is built using ROS nodlets. So I mentioned about the advantage of using ROS nodlets. ROS nodlets are like it can publish things without spending much bandwidth. Okay, it's like shared memory architecture, so it doesn't consume the bandwidth, network bandwidth. So the publishing and subscribing is basically using shared pointer. Okay, so here you can see it is mainly taking the Velodyne point cloud and then using that. I mean the input will be other input will be odometry, GPS, IMU, and yeah, so all these things are the input, and the output will be the 3D map. Okay, so I will prefer you to download this. It's actually very simple to set up. You can I think, let me check, it is compatible with Noitic. I think it will be. So just go through the, yeah, so here you can see the setup instructions. Yeah, I think it will work with the Noitic. So just try with these launch files with the back file. The launch files and back files are given. So you can see the 3D map building using this back file. Okay, and there is an outdoor map as well. Okay, this map is actually creating based on the LiDAR. Okay, LiDAR data. Okay, and they are also like giving a data set for with the GPS, so you can actually try it out. So these are the important packages for the HDL graphs. Uh, like there is a SLAM algorithm, and also there is a localization algorithm. So the localization algorithm help to localize on the 3D map, and they're also like giving the people tracking, because for the self-driving vehicles, I think people tracking is also important, right? So everything is mentioned, like the base paper is mentioned, then the packages, then the node description, and even the back files. Okay, so this slam is mainly based on a thing called NDT. So I think that is um, let me check, that is yeah, so it is given here. It is based on 3D graph slam. It's a graph slam with NDT scan matching. Okay, so NDT, which is actually the technique for the scan matching. You can see here it is mainly using the self-driving cars. So this is one of the common technique that we are using in the self-driving cars. So that's why I mentioned the NDT based thing. And like other SLAM algorithm, I think it is having all the inputs, GPS, IMU, that is necessary for a self-driving car vehicle. Okay, so you can actually test it. Okay, I think one class, I think it was RDLP 1.0. I have actually demonstrated it. It's not a big deal. Just download the back file and launch this launch file, and you can see in real time this map is building. Okay, yes, so you can have a look onto it. This is a base paper. Okay, the HDL graph slam. Okay, so I think we have covered some of the 2D and 3D slam techniques. I think we can conclude the session, conclude the chapter as well. And if there is anything missing, we can discuss later. So after this chapter, I think maybe I can jump into the legged robots. Maybe we can see some interesting simulation and navigation of legged robot. Yeah. So let me know if you have any question, guys. For this session, I think we have discussed some 2D and 3D mapping. So let me know if you have any question. Any questions? I think you got the idea, right? So maybe I can conclude, and then for the next session, I will announce a date. Okay, I will announce a date. So mostly we will be discussing with the ROS and lect robot. If there is any change, I will be mentioning. Okay. Okay then, guys. So if you have any question, you can put it in the discussion channel. I will be supporting you. Okay. Okay, everyone. Good night. See you next week. Okay. Bye.